Hello, welcome. Thank you for attending. I'd like to begin by thanking Micah Chrisman in particular for the invitation to present in the seminar, along with all of the other co-organizers. So let's go ahead and begin. The title of my talk today is kind of a lot of title. So I'm going to show to you that links in homology spheres are all homotopic to slice links. And the way I'm going to show you this is a nice geometric trick, which we've taken to calling the relative Whitney trick. This is a joint project with Patrick Orson and Jungwon Park. So what am I going to do today? Well, I'm going to begin by telling you exactly what I mean by calling a link in a homology sphere homotopic to a slice link. As soon as I do that, I'll give you a precise statement of the main theorem, though in some sense it's up in red at the top of the screen right now. Now this result, that links in homology spheres are all homotopic to slice, is really an old result, at least for knots. Old in the sense that it comes from before the turn of the century. Austin and Olson proved it in '99. And I'm going to recall for you exactly their proof. Well, a brief summary of their proof. Because the proof that I'm going to present will be fairly similar. The key difference will be that a condition that they used due to Friedman and Quinn doesn't apply to links, but just last year was published a new sufficient condition for sliceness of links, which we will use. And then in order, the last ingredient we'll need is this relative Whitney trick. And once we're armed with all of that, I'll be able to prove the theorem in red at the top of the screen. So, slice links in S3. So maybe I should motivate the definition before I actually make it. A thing that I've been finding myself interested in quite a bit recently is the difference between knot or link for today, concordance in S3, and the same theory for knots or links in homology spheres, or in general for knots or links in any three-manifold. So what is the core question of knot or link concordance is this. Given a link in S3, does that link bound a collection of disjoint embedded disks in the four-ball, and either you'll require these disks to be smooth if you want to do smooth knot concordance, or just locally flat, meaning that these disks will have tubular neighborhoods if you want to study topological concordance. More precisely, a link is called smoothly or topologically sliced if it bounds such a collection of smooth or locally flat embedded disks in the four-ball. Now, I'll be interested in the topological setting today, meaning that, in general, whenever you see an ambiguity about what sort of embedded disks I'll be looking for, you should assume that I mean the disks to be locally flat. There will be a few exceptions, and I'll try to make it totally explicit when those exceptions appear. So, there's a definition for knots or links in S3. I want to study knots or links in an arbitrary homology sphere. Let's go ahead and be totally explicit about what that means. When one says that a link in a three-manifold is slice, they're being a little bit ambiguous. They're saying that that link bounds some embedded disks in a specific four-manifold, maybe a specific type of four-manifold. And so I'll have to make totally explicit what I mean for a link in a homology sphere to be sliced. I need to tell you what four-manifold I want to look in. Well, by walk of Friedman-Quinn, there's a natural choice. Any homology sphere bounds a unique, contractible, topological four-manifold. It might not admit a smooth structure. By the four-dimensional Poincare conjecture, in fact, B4 is that unique, contractible four-manifold bounded by S3. So there's a good analogy of the four-ball for any given homology sphere, namely that contractible four-manifold. So the definition I'll use for what it means for a link to be slice is I will say a link is slice if it bounds disjoint, locally flat, embedded disks in the contractible four-manifold bounded by Y, and I'll try to be consistent and denote by mathcal B sub Y that four-manifold. So here's, if you like, the meta question that I want to ask. Pick a property of links in S3 which has something to do with slices. That's super vague, but that's okay. does that property hold for links in homology spheres? And that's so very vague that here's an example of what I mean. Any knot in S3 bounds a locally flat embedded disk, namely take the knot, take its cone. Now that disk is very much so not smooth or locally flat at that one bad point. Maybe a picture will be convincing. So if there's supposed to be a picture of S3, maybe I'll draw it as S2. I can't draw four-dimensional things. And there's the knot K, drawn down a dimension. Then the cone on K. There it is. And if you look close to this cone point, you'll see a point where that disk is not flat. So this isn't a smooth or locally flat disk, but nonetheless, any knot does bound an embedded disk. So what Selman-Akbulut did in 1991 is he proved that there is a knot in a homology sphere which, even though that homology sphere does bound a contractible four manifold, there's a knot in that homology sphere which does not bound a piecewise linear embedded disk in that particular four manifold. It does, however, in another contractible four manifold bounded by that same homology sphere. In 2016, Adam Levine proved a different result. He produced a knot in a homology sphere, which, even though that homology sphere bounds a smooth contractible four manifold, that particular knot does not bound a piecewise linear embedded disk in any contractible four manifold bounded by that homology sphere. So he proved that between these two results, the property in red, this property, fails very badly if you extend it in a natural way to knots in homology spheres. So here's the property of knots, or links in this case, in S3 that I want to study for links in homology spheres. Any link is homotopic in the sense that as a function from the disjoint union of a bunch of S1s into S3 to a slice link. So that's obviously true. You can take a link and make a bunch of crossing changes and eventually get down to the unlink, which certainly does bound a smooth, in fact, embedded disk. So here's the question. Is the same true for links in homology spheres? Now, since a homology sphere other than S3 won't be simply connected, you can't make the same argument. A link whose components are not homotopically trivial, as in 0 and pi 1 of the 3 manifold, has no hope of being homotopic to the unlink, but maybe it'll be homotopic to a slice link, a link that bounds an embedded disk in the unique contract 4 manifold bounded by Y. As a partial smooth answer to this question, if you happen to study a homology sphere Y, which bounds a contractible 4 manifold, so that that contractible 4 manifold has a handle structure which has no 3 handles, then any link in that homology sphere Y will be homotopic to a link which bounds a disjoint union of smoothly embedded disks in this 4 manifold W. Now, I'm not going to prove that result today. Instead, here's what I'm going to show you. In the topological setting, it's a much more absolute answer. Any link in any homology sphere is always homotopic to a topologically slice link. Now, for knots, this result is fairly old. As I said, it's due to Austin and Olfson in a paper published in 1999. They proved that any knot in any homology sphere is always homotopic to a slice knot. Now I'm going to recall the argument they use because I'm going to use an argument that's very similar. Now the first ingredient that's important for their proof is a fact due to Friedman and Quinn from 1990. Namely, that's the fact that the Alexander polynomial detects free sliceness, and that's true even for knots in homology spheres. Namely, if you have any knot in any homology sphere, then the Alexander polynomial is a unit in the ring z of t inverse, if and only if that knot is freely sliced. And maybe I'll tell you what this word free means. This word free means that the fundamental group of the contractible form manifold minus a neighborhood of the slice disk is freely generated by the meridian of the knot. So there's a strategy here. You need to figure out how to take any knot in any homology sphere, change it by a homotopy, to get something whose Alexander polynomial is this. So let's recall how to compute the Alexander polynomial. So let F be a Seifert's office. The Seifert form is a bilinear form from the first homology of that Seifert's office across the first homology of that Seifert's office to the integers, given by taking two classes in H1, representing them by curves in F, pushing one of those curves off of the Seifert's office in the positive normal direction, leaving the other one alone. That now gives you a two-component link in a homology sphere. Compute the linking number. The Alexander polynomial is given by representing that form by a matrix, by picking a basis, and then doing this, computing the determinant of V minus TV transpose. So here's the game then. Just pick a basis, may as well make it a symplectic basis, and then figure out how to homotope the knot and the Seifert's office along with it until you can get that Seifert's office to be as simple as possible. And I'll give you a picture of how to do that. So suppose you find a couple of curves in your basis. Say these are two of the basis curves you've chosen. And let's suppose that the linking between AI and AJ plus, so remember that's going to be the IJ entry in this matrix V. Let's suppose that's not 0. You would like it to be 0. So here's the game. Find a little arc, that's the little green piece that intersects both of those curves transversely in a single point. Take a little neighborhood of that arc. Well, that is a small 3-ball inside of Y that intersects the Seifert's office in that little blue rectangle you see right there to the left. And just do a homotopy that is supported inside of this small 3-ball by doing exactly that. And you see this has changed it so the blue curve has its linking with the red curve increased by 1. You could do something similar to reduce it by 1, or do anything else. So you can change the Seifert matrix to anything you want. In particular, you can change the Seifert matrix until you can get it down to this. So now you have reduced this knot by a homotopy to a knot whose Seifert matrix looks like this. Take V minus TV transpose and take the determinant. You'll wind up with plus or minus a power of T. So by the result of Friedman-Quinn, this knot that you'll land on after this homotopy is freely slice. And that completes the proof that Austin and Olofsson used. So if I want to imitate that proof, here are the ingredients I need. I need a sufficient condition for a knot to be, a link, rather, to be slice. There's the first thing I need. Then I need to figure out some way of imitating this analysis, this homotopy. I need to find a way of homotoping an arbitrary link until I get something that satisfies whatever the assumption of this sufficient condition for free sliceness is. So let's try to do exactly that. So what is this sufficient condition for free sliceness? Well, here it is. Recently proven just last year by Jae-Chun Cha, Min-Hoon Kim, and Mark Powell. If L is any boundary link in S3, so what is a boundary link? A boundary link is a link whose components bound a disjoint collection of surfaces in S3. That collection of disjoint surfaces is called a Seifert's office. If that Seifert's office has a symplectic basis, well, any orientable surface does. But the additional condition is that for every J between 1 and G, the genus of the surface, the link consisting of AJ together with all of the positive push-offs of the BIs, is link homotopically trivial, and the link you get by starting with any of the BJs and then taking all of the push-offs of the BIs is also link homotopically trivial, then the link itself is freely topologically slice. Now, I'll explain some of the WODs, namely link homotopy, right now. So a link is link homotopically trivial if there is a sequence of self-crossing changes reducing that link to the unlink. And as a remark, this is not what I've been referring to as homotopy of links in the past. So this is stronger than what I've been calling homotopy. And that's because of this assumption that it has to be self-crossing changes. So I'll allow a homotopy in which you can pass any component of the link through itself, but not through any other components. Nice. So you'll notice that this is a condition on links in S3. I want a sufficient condition for free sliceness, well, just for sliceness would make me happy enough, which applies to links in any homology sphere. Well, the first thing that you'll need is, what should link homotopically trivial mean for a link in a homology sphere? Well, there's a good answer. So here's a result. A link in S3 even is link homotopically trivial if and only if that link bounds a disjoint union of Morse disks in the four-ball. And that follows fairly straightforwardly by thinking about the trace of a homotopy. So here's the game. If you replace this word link homotopically trivial with this notion of 4D homotopically trivial, then you'll get a theorem which you can ask if it's true for a link in a homology sphere. And it turns out it is. So here's the Cha-Kim-Powell theorem stated again. And here's the theorem that we've proven, that I won't prove in this talk. Let L be any boundary link in a homology sphere Y. If that link L bounds a Seifert's surface, again, just a disjoint union of a bunch of oriented embedded surfaces in Y, bounded by the components of L, which admits a symplectic basis, so that for every J, this G plus 1 component link and that G plus 1 component link are both 4D link homotopically trivial. There's an inconsistency. On the previous page, I didn't say link homotopically trivial. You'll have to forgive that typo. If that is true, then the link L is freely sliced, meaning that the link bounds a disjoint collection of locally flat embedded disks in the unique contractible Four manifold bounded by Y, and the complement of that disjoint union of disks has free fundamental group freely generated by the meridians of L. So 4D link homotopically trivial. Again, maybe I shouldn't have the word link there. A link is 4D homotopically trivial if its components bound a bunch of disjoint Morse disks, not in the four-ball, but in the analog of the four-ball for this homology sphere Y. The proof of this theorem is the exact same as the proof presented by Cha-Kim-Powell, so I won't go through it. It's a good example of the use of surgery to solve questions in low-dimensional topology. I won't prove it here. So, modulo this theorem, what do we need to do? We need to find a way of starting with a link in a homology sphere and homotoping it until it satisfies the assumptions of the theorem at the top of the screen. Namely, I need to take an arbitrary link and then turn it into a boundary link. Moreover, I need to turn it into a boundary link which admits a Seifert's surface admitting a symplectic basis, which satisfies that for every J, these two G plus 1 component links are 4D link homotopically trivial. So here's the key lemma. Any link in a homology sphere is homotopic, not link homotopic, just homotopic, to a 4D homotopically trivial link. That is, to a link whose components bound disjoint, immersed, not embedded, just immersed, disks in the unique contractible Four manifold bounded by Y. And the way that I'll go about proving that is a trick called the relative Whitney trick, which I'll present immediately. So what is the relative Whitney trick? Well, maybe I should start by telling you what the honest Whitney trick is, since the relative Whitney trick is supposed to be some sort of relative generalization of the Whitney trick. So, the Whitney trick. So the goal is to find 2 points which look like they should cancel in the intersection of 2 surfaces in a four manifold, and then remove those 2 points of intersections by changing the surfaces by a homotopy. So here's the precise setup. Let S1 and S2 be Amorth surfaces in a four manifold, which intersect transversely in points P and Q, and those 2 points should even be points with opposite sign, intersection points with opposite sign. Next, find some arcs in these surfaces connecting these 2 points. Namely, there's an arc A1 in, I guess this surface is S1. Find another arc A2 sitting in S2. This picture is obviously slightly dishonest. It needs to be three-dimensional so I can actually draw it. But this should give the idea. If the concatenation of those 2 arcs bounds an Amorth disk in the four manifold, which satisfies some framing condition, then that disk will be called a Whitney disk. And that framing condition is just what you need to make sense of this next picture. Take 2 parallel copies of that disk and use those 2 parallel copies of the disk to push S1 over that disk. That removes those 2 points of intersection. So do exactly what this three-dimensional picture is suggesting. Now there are a few cautions you should have. One of them is that you might add a new point of intersection. So if you have some other surface which intersects the Whitney disk transversely in a single point, then making this move will increase the number of intersections between S1, remember this big one was supposed to be S1, and that new surface by 2. We've introduced 2 new points of intersection. So this trick works really well in high dimensions, and it gets used in proving the Whitney embedding theorem and the H-cobordism theorem. So let's give this relative generalization. So here's the idea. I want to get rid of a single point of intersection between 2 surfaces at the possible cost of changing the boundary of these surfaces by a homotopy. Well, let's give the setup. Let's let S1, there's S1, and S2 is supposed to be this surface. Let's suppose those intersect at this point P. Let's pick a point Q1 in the intersection of the boundary of S1 with the boundary of W, and Q2, a point in the intersection of the boundary of S2 with the boundary of the four manifold W. And then we'll find the arcs that are already highlighted in blue. Find an arc A1 from P to Q1. Find an arc A2 from P to Q2. And then find a third arc A3 in the boundary of W connecting Q1 to Q2. And orient these curves so that the concatenation A1 star, A2 star, A3 bounds is a simple closed curve. If that simple closed curve bounds an Amorth disk delta in the four manifold W, then I'll call this delta a relative Whitney disk. And you'll remember that there was a framing issue that I kind of glossed over on the previous slide. There's no such framing issue. Any such Amorth disk is a relative Whitney disk. Meaning that if you start with any disk, you can do this trick. You can take 2 parallel copies of that Amorth disk and use those 2 copies to push S1 over the disk to get rid of this 1 point of intersection. So there used to be a point of intersection here at P. Now I've changed S1. That point of intersection no longer exists. There's the same danger as there were before. You might introduce new points of intersection if something intersects that relative Whitney disk, say maybe S2 did, then when you do this move, you'll increase the number of intersections between S1 and whatever that new other surface was. So you need to be careful when you do the relative Whitney trick. just as you did when you used the Whitney trick. So go back to thinking about the lemma. I want to use this trick to start with a collection of embossed disks and homotope them while changing their boundaries to get disjoint embossed disks. I want to get rid of all intersection points. So let's go ahead and do that. Let's take an arbitrary link in a homology sphere and change it by a homotopy, not a link homotopy, any homotopy, to a 4D homotopically trivial link. And first I'll give the proof in the case of 2-component links, then I'll give the proof for 3-component links. Once you know the proof for 3-component links, you'll have a pretty good idea what the proof for n-component links should be. So, step 1, let's find these embossed disks. The fundamental group of math cal by, the unique contractible four manifold bounded by y, well, it's contractible, so pi1 is 0. So any link bounds embossed disks in this four manifold. Find a point of intersection in D1 intersect D2. If there were no points of intersection, you would already be done. So find any point of intersection. Find a relative Whitney disk. I assert you can. So how? Well, find an arc in D1. Remember, D1 is an embossed disk, so you can find an arc from that point to a point on the boundary. D2, also a disk, so you can find an arc from that point to a point in the boundary of D2. Find any curve in the boundary of y connecting those 2 points. Oh, and then, hey, the fundamental group of math cal by is 0, so that black circle that I just drew bounds an embossed disk. It's null homotopic. Now, there's a problem. Maybe there's a little bit of D2, namely this green surface, which intersects the relative Whitney disk. If that's the case, then doing the relative Whitney move won't help me. Sure, it'll get rid of this intersection point at P, but it'll create at least 2 new points of intersection. So the number of intersection points between D1 and D2 will actually increase, which would mean that this procedure is taking me further away from finding disjoint embossed disks. So I need to show you how to remove these points of intersection between the relative Whitney disk delta and the embossed disk D2. And that move is going to be a finger move. So here's a cartoon picture. So here is the relative Whitney disk delta. Here's D2. And again, there's maybe some subtlety about how to interpret this 3-dimensional picture as a 4-dimensional picture. Well, here, I'll tell you how. So I'm going to find a little arc from this point of intersection to the boundary of D2. That little arc has a neighborhood in math cal by homeomorphic to a 4-ball, but that 4-ball is the same thing as B3 cross -1, 1. And you should picture everything happening in this picture being in B3 cross singleton 0, except for that green piece. This green piece you should trace through I guess it's pink now. So I'm going to use this little arc, who I didn't name, to change what B3 looks like. And here exactly is what I'll do. I'll just push it over that arc. You'll notice this creates 2 new points of intersection between D2 and itself. There are 2 new double points in D2. But remember, I'm just trying to find disjoint embossed disks. I'm fine with increasing the number of double points. So after you remove all of the points from D2 intersect delta by increasing the number of double points of D2, well, now you're set up to perform the relative Whitney move. So perform the relative Whitney move. This number will decrease. So something that I didn't do was remove points between D1 and the relative Whitney disk. So I might increase the number of double points of D1. That's just fine. In fact, the relative Whitney disk had no reason to be embedded. It may have been embossed. every self-intersection point of the relative Whitney disk is going to introduce 4 new points of intersection, self-intersection in D1. But again, I don't care about self-intersection points. I'm just looking for MOS disks anyhow. So that tells you how to remove 1 point of intersection. We'll repeat this same argument at every point in the intersection of D1 and D2, and then you're done. So for a 3-component link, the argument is more subtle, but not much more subtle. So we'll start by doing exactly the same setup. Since this thing is simply connected, the components of this link, it's a 3-component link now, bound MOS disks. If they were already disjoint, you would be done. Find an intersection point in 2 of them. Associated to that point of intersection, you can find a relative Whitney disk, delta P. That's this blue disk is right now being called delta P. This point of intersection was called P. And I'm calling it delta P because there's going to be another Whitney disk that will show up. So I already know how to deal with points in delta P intersect D2. Namely, that was this finger move business. Points in delta P intersect D1 are fine in the sense that if you perform the relative Whitney trick, then points in delta P intersect D1 will just increase the number of double points in D1, but that's just fine. So the only bad thing that happen is delta P might intersect the third component of this union of disks. If it does, then when you perform the relative Whitney move, the number of intersection points between D1 and D3 might increase by 2. So here's the solution. We'll find a higher order Whitney disk, delta Q, and we can use finger moves, just as we did on the previous page, to arrange that delta Q intersect D3 is empty. That'll produce lots of self-intersections in D3, but again, we're okay with that. So, summarizing what we have so far, we found a point in the intersection of D1 and D2, which we would like to get rid of. We found an associated relative Whitney disk. We found a point in the intersection of that relative Whitney disk with the third one of these MOS disks, D3, and found another relative Whitney disk, delta Q, associated with that point of intersection. The intersection between delta Q and D3 is now empty, and how did we do that? Well, we did finger moves. And let's see how to proceed from here. So first, use the relative Whitney trick to reduce delta P intersect D3 by 1. So that is, I want to remove this point of intersection. How do I do that? Well, I find a little neighborhood of that green disk, and I change the blue disk by pushing over that neighborhood. And I didn't generate that picture electronically because it was just too hard to do, and I don't think the picture would have been that helpful anyway. The point is that you can now get rid of that point of intersection. That increases the number of double points in delta P, but that's fine. We'll iterate until delta P intersect D3 is empty. All right, cool. So now we have delta P intersect D3 being the empty set. Delta P might still intersect D2, but we already saw what to do. Just use finger moves to get rid of all the points in delta P intersect D2. Now you can use the relative Whitney trick to get rid of this original point of intersection while preserving the number of intersections between D1 and D3 and D2 and D3. And now just iterate that at every bad point, at every point of intersection. So notice this is going to uncontrollably increase the number of double points, but we don't care. So the proof for more components is going to be the same. The only difference is there will be some more bookkeeping. Right? So maybe you have D3 intersecting the relative Whitney disk, in which case you find a higher order relative Whitney disk. But maybe you have a piece of, picture is bad now, D4 intersecting that. Well, you'll find a higher order, a third order relative Whitney disk to get rid of that. So the basic philosophy is, whenever you see an intersection move that you don't already know how to fix by a finger move, then find a relative Whitney disk. And every time you increase the depth of these relative Whitney disks, you increase the types of intersections that you know how to deal with. Since there are only finitely many disks in the original union of disks, eventually you can deal with all of the types of intersections. That's vague, but hopefully that philosophy makes sense. All right, so we've now proven this lemma. Maybe we'll call it for you right here. Any L contained in a homology sphere Y is homotopic to 4D homotopically trivial. There's what we just proved. I need to use that lemma to prove that a link in a homology sphere is homotopic to a slice link. That's my goal. Now I'm going to do some stuff to walk towards that, but here's the actual conclusion I'll make at the end of this slide. I'll show that any link is homotopic to a link which has the property that the link, together with its zero-frame pushoff, is 4D homotopically trivial. So let's go ahead and do that. So for starters, Y is a homology sphere. So that means that the link you start with is null homologous. So it's a commutator in the fundamental group of Y. So you can use that to construct a Seyfart's office. I'll call it sigma. In fact, that Seyfart's office sigma will satisfy that it has a symplectic basis consisting of AIs and BIs. Maybe this is A1 and B1, this is A2, B2. In particular, all links are homotopic to boundary links. You'll recall that when I said how we were going to use the Cha-Kim-Powell theorem, that was one of the things we needed. We at least have any link being homotopic to a boundary link. Well, but check out these alphas and betas. Oops, I called them A and B down there. By the homotopy trivializing lemma, we can change these alphas and betas by a homotopy, and eventually find that if you take the union of all of the alphas and betas, zero-frame pushoffs done to the betas, these things will bound disjoint embossed disks. And changing the alphas and the betas, well, this L is exactly a commutator, at least in pi 1. So changing the alphas and betas will just change the choice of L you have by a homotopy. You need to be a little bit concerned with base points to figure that out, but I think that's a believable enough fact. And now I claim that this is everything you need to saw draw sigma and sigma plus to get the consequence, which is right now at the bottom of the slide. And let's zoom in and say exactly how to do that. So remember that red curve was supposed to be one of the BIs. So here's what I'll do. Take the sophis sigma, that's the black sophis, push it off of itself to get sigma plus. So that's this sophis. It's supposed to be like sitting on top of sigma. On there, I see a copy of BI plus. BI plus, beta I plus rather, bounds an embossed disk. So I'll take sigma and I'll cut out a neighborhood of BI and glue in 2 copies of this embossed disk. And I'll do that at every one of these BI pluses. I'll change sigma by gluing in one of these embossed disks. And remember, these embossed disks are allowed to have self-intersections, but they'll be disjoint from each other. So once I do that, I'll have replaced each component of sigma plus with an Amos disk, and all of those Amos disks will be disjoint. Now I'll do the same thing to sigma, except I'll use these AIs. So these things also bound Amos disks. These are cartoons of what an Amos disk should look like. So I'll take sigma, I'll cut out tubular neighborhoods of all of the alpha i's, AIs rather, and I'll replace each of those annular neighborhoods of AI with 2 copies of each one of those Amos disks. Oh, but check it out, all of the Amos disks were disjoint, so I haven't introduced any intersection points between different components of sigma when I've done that, and I've now sorted all of the sigmas down to disks. So that means that the link that I've started with has been homotoped to a new link called J, which has the property that J together with, so there's J, there's J plus, the various components of J union J plus are now 4D homotopically trivial. They bound a bunch of disjoint Amos disks. All right, well that wasn't the theorem. I wanted to prove that any link in a homology sphere is homotopic to a slice link, but that'll be relevant for the next slide when I'll actually prove the theorem. So, again, I want to show that any link in any homology sphere is homotopic to a slice link. I'll use that consequence from the previous page. And how will I use it? I'll use it by saying most of the same words on the previous page. Any link is null homologous in pi 1. So you can use that to build a Seyfart's office bounded by the components of L with exactly those alphas and betas as a symplectic basis. By the previous page, I can change these alphas and betas by a homotopy and eventually get this thing to be 4D homotopically trivial. Doing so will only change the link L by a homotopy. Oh, well, let's keep track of what we've done. So I've taken L, I've changed it by a homotopy to get a boundary link, right? I've got a Seyfart's office, so it's a boundary link. That boundary link, that Seyfart's office rather, has a symplectic basis consisting of alphas and betas, so that this big 4G component link is 4D homotopically trivial. In particular, if I take these sublinks, I'll get something that's 4D homotopically trivial. Oh, but hey look, I've just satisfied all of the assumptions in the Cha-Kim-Powell theorem. So, L is homotopic to something that's freely slice, in fact. Neat. So that completes the proof of the main theorem. There are just a few more things I want to say. Namely, I want to close with some related questions to this that are maybe worth thinking about. Maybe I'll close with just a few So let's do that. So I'm going to make some observations and give some related questions. So here's one observation. In the proof of the thing that I called the homotopy trivializing lemma, whenever I undid a point in the intersection of 2 Amos disks, all that I changed the original link by was a single crossing change between the associated components of the link. So as a consequence, you get the following result. The minimal number of intersections between Amos disks bounded by L, so take any collection of Amos disks bounded by the components of L, compute all of the intersections between those Amos disks, sum them up, take the minimum over all collections of Amos disks. That is the exact same as the minimum number of crossing changes needed to transform L to a 4D homotopically trivial link. So I'll call that number either that count of the number of intersection points between disks or the number of crossing changes needed. I'll call that n of L, the homotopy trivializing number. Well, here's a question. What is n of L? Or maybe as an imperative, compute n of L. And there are some surprising answers that one can get. So for a 2-component link, n of L is the same as just the linking number. If you like, that's because you can get the linking number down to 0 by crossing changes. You can change one crossing and change the associated linking number by 1. And linking number is a complete 4D link homotopy trivial abstraction. So as soon as you get down to linking number 0, a two-component link bounds disjoint Morse disks. For the case that n, the number of components m, is equal to 3, well, first you have to get rid of all of the linking numbers, so you have to make at least that many crossing changes to get down to link homotopy trivial link. But once you get down to something that has 0 linking number, you might still have non-vanishing triple linking number. But it turns out you can get rid of triple linking numbers, no matter how big the triple linking number is, by a total of 2 crossing changes. So for any 3-component link, the homotopy trivializing number is somewhere between the sum of all of the linking numbers and the sum of all of the linking numbers plus 2. In general, for any m-component link, the difference between the homotopy trivializing number and the sum of the linking numbers is a constant. It's something that depends only on the number of links, only on the number of components of the link. For m equals 2, C2 is 0, C3 is 2. In general, I don't know how big C4 is even. So how big is that constant? So the next observation to make is this is kind of a 4D analog of Dane's lemma. So you'll recall Dane's lemma, maybe a little informally, says that if you have a curve in the boundary of a 3-manifold, then that curve is homotopic to a curve that bounds an embedded disk in that 3-manifold. Now, the result of Austin and Wolfson that I presented almost a full hour ago now is kind of exactly that. If you have any knot in a homology sphere, that's the boundary of a contractible 4-manifold, that knot is homotopic in the boundary of that 4-manifold, something that bounds an embedded disk. So here's a question. How important is it that you use a contractible 4-manifold? If you have any knot in a 3-manifold that's null homotopic in some 4-dimensional filling of that 3-manifold, then does it follow that that knot J is homotopic to a new knot which bounds a smooth or locally flat, pick your favorite category, embedded disk in W? And ask the same thing for links. I don't know the answer to that question, but I think it's an interesting question to ask. Wonderful. Well, thank you for your attention. I'll see you on February 8th.